webinar that is focused on image-based monitoring of pests and disease for smart agriculture application. Today's webinar will give a first short introduction about COMMECT by myself. I'm Maria Rita Palattella, and I'm the project coordinator. And this intro will be followed by two dedicated speech, one more related to drone-based camera and also mobile picture that are used for monitoring a vineyard by Miriam Machwitz and Mario Gilcher. And we will continue instead with the second talk that is more related to image trap data for pest monitoring in olive tree farm, and this is given by Mehmet Hakan. So we will conclude the webinar with a Q&A session, and you are welcome to join the discussion. So before we start, I would like to share with you some housekeeping rule. We kindly ask to mute yourself and keep the camera off. And we have a Q&A chat session where you can write your question while the speaker are presenting, and we will take all the questions in the end. And we kindly ask to also raise your hand in order to join the discussion. As you have been already informed, we would like to record this webinar, and in this way it can be made accessible also to others outside this time frame, and it will be shared on our project website. So for those that don't know about COMMECT is an Horizon Europe project that started more than 2 years ago. It was acquired in the Cluster 6 call, focusing on community, and the aim of COMMECT is about connecting rural community and extending connectivity in rural remote area. As we all know, the digital divide still persists. The rural areas are still largely unconnected, but there is a need to make an effort and to connect also this area to support the rural community in the digital transition. Clearly, if there is no connectivity, no network coverage, it is impossible to enable any digital service and application. So this is now clear and well recognized by the European Commission, and there is a need to put an effort in extending the coverage in remote area. In COMMECT, we have adopted a bottom-up approach, and so we establish 5 living labs in and across Europe. We have one in Luxembourg related to viticulture, one in Norway related to connected forests, one in Denmark for livestock transport, one in Turkey for olive tree farm, and one in Serbia about sustainable agriculture. In all of them, we are investigating a different connectivity solution that include terrestrial network, but also satellite. So not terrestrial network like drone and satellite. The first year of the project was fully dedicated to understand the need of the rural community and see how, thanks to the new digital application and the connectivity solution, we can support them. And you can see that in general, there is a need of better monitor microclimate condition, and this is a common need of Luxembourg and Turkey, and it will be the focus of today's webinar. But there are different needs, for instance, for the forest sector, where drone could help, for instance, situational awareness, or 5G private network could support provide support to the operator, and in Serbia there is a need in general of having a shared digital infrastructure. So in all the living lab, we identified the common need of transmitting sensor data, and for this we can use several IoT protocols like LoRa, BIoT, and LTM. But in other case, we need to acquire image or video, and for that we need 5G private network, or we need drone, or we need satellite day calling. And this is part of the discussion today, and I will hand over to my colleague Miriam.
So thank you very much, Maria Rita, and a very warm welcome from my side. Please mute your microphones if possible. I have the pleasure to introduce you into the Living Lab Viticulture. Today I will show you one part of our Living Lab, mainly related to image data. But our Living Lab is divided or represented by two use cases. One is more focused on plant protection, where we have weather stations in the field, which are then transformed with advanced connectivity solutions to have a better forecast of disease severity. And the second part is more related on monitoring by image data, different sensors. Here we can support site-specific activities on the one hand, but also have a digital tool, a digital representation of the vineyards, which is mainly part of today's webinar. This image observation can be divided into three scales. We have the plant scale, where we have really in the field cameras passing by a tractor to have observation of the plants. Then we have the bird eye perspective with very high resolution, represented by the drone or UAV scale. And then, which we will not tackle today, we have also a regional scale, where we can observe the entire region with satellites, for example, to analyze patches or structures for drought stress. So why do we need this? What is the added value for the wine grower? So digital plans or digital representations of the vineyard can be used for site-specific management. We can have also very let's say special applications like the Esca monitoring, which I will explain a bit more in detail, and which replaces the marking in the field, which is also bringing microplastic in the soil, which is a larger problem for viticulture. And we could also monitor, for example, dead or missing plants for the replanting of single vines. So this example of Esca, what is Esca? Esca is a trunk disease where you have fungi in the trunk, and this develops these typical symptoms with these tiger stripes you can see on the left side. And this appears on single plants and rather randomly over the field. And you have different measures, like, for example, trunk surgery or reset, which, as said, you don't apply on the entire vineyard, but on single fields. And with this high-resolution monitoring, you could do this in winter, which is recommended because it's not so warm, but you cannot see the symptoms anymore. But with such a digital vineyard, you can go to your plants and apply these also work-intense and costly measures only on the plants where it's needed. And with this, I would like to hand over to my colleague Mario Gilcher, and I stop sharing.
Okay, hello to everybody from my side. I'm Mario Gilcher. I work for LSC 360, and we specialize on geospatial monitoring of, for example, construction sites, of forests, of agricultural sites. And I'm going to show you now innovative approach to plant disease monitoring based on smartphone data. So Miriam has already outlined the importance of Esca monitoring and digital twin for vineyards. Just to outline the problem a little bit, we have usually ground truth data, which can be anything. It can be the detection of a certain disease on a leaf, or it can be an expert-based rating of the plant or the soil. But usually that comes with kind of lower spatial accuracy. So for example, we just have a GPS measurement which has a high spatial error, or we have something like an ID of the plant, which is common in monitoring vineyards. So you have the row ID, so you know in which row you are, and you have a plant ID counting the plants. So basically you have a rough idea where a certain assessment was taken, but it's, as I said, very rough. But when we do monitoring based on imagery, like UAV imagery or satellite imagery, this is often not enough because we have to know exactly where, for example, a leaf symptom happens in order to analyze it with or to cross-reference it to an orthomosaic, so we can see exactly how a symptom looks like from the UAV perspective or from a satellite perspective. And this is not possible if we have low spatial accuracy. So the idea is to bring the two together. By basically using very, very high spatial accuracy smartphone imagery acquired with a smartphone plus antenna, and then do image-based segmentation with AI, so we know exactly where certain features are in the image, and so we collect the data, we do our AI-based image analysis to segment the image into certain features, like for example leaves, stems, diseases, grapes, and so on. And then we do photogrammetric reconstruction, which basically means that due to detecting tie points between the images, we align them in 3D space. So we know where each image was taken and where each image is looking at. And therefore, we know, roughly speaking, where each pixel on each image is in 3D space. Which means basically we get geo-referenced point clouds with semantic information. So we have a point cloud that has, of course, RGB colors, so green, and so we know, for example, we can easily see where the leaves are. But on top of these RGB colors, we have semantic information. For example, semantic that each point belongs to a certain class, like stem or disease or fruit or whatever. It can be arbitrary. And based on these geo-referenced point clouds, then we can derive very, very high level products, like for example, precise locations of the stems, precise location of certain leaf diseases, and so on. Yes, so to give you an example here, we have a video of how that looks like in the field. I don't know if you can hear the audio. It's actually very loud. Audio is not important here. So you have an example of such a system. We have here the two devices, actually. I can stop right here. This gray little thing sticking up is the antenna. It's mounted on the tractor, and we have twice looking in two directions. And then on the antenna mounted is a very basic smartphone that has taken a video and is connected to the antenna. So we know basically for each frame of this video where and when it was taken. And we have therefore a very high spatial accuracy. Yeah, and then the tractor we have here a test run without leaves, obviously. So this is just to give you an idea of what this device looks like in action. But it can also be taken by hand, or so it's very flexible. Yes, and then we have the setup of the COMMECT project, which is basically satellite backhauling, and the satellite backhauling is connected with a Wi-Fi access point on the tractor, and the smartphone is connected to this Wi-Fi repeater, and then can therefore repeatedly upload these videos, which gives us a lot of flexibility in the field, because these videos, they can have varying quality. So we can take very low quality videos with something like 640 by 480, or we can take full HD videos, we can take 4K videos. So this is supposed to give us a lot of flexibility to upload data in the field, and therefore begin processing much quicker. Yes, so to show you what this then looks like, here you can see a visualization in the app. So what you can see here on the right is one image taken by the tractor, and each point here, each of these blue, violet to yellow points is an image taken with a smartphone. And in the background here in green and red, we have field data from an expert. So experts were rating each plant if there has been Esca detected on a given plant or not. And this is taken on a vineyard in Luxembourg. Yeah. So for each image now, we go ahead and try to detect Esca on the leaves. And if there's nothing detected, they look violet, like you can see here. Yes, so that's that. Then you can go out a bit, and then you can see you have a few yellow hotspots here and there, which means that Esca has been detected, and we can zoom in a little bit and see how that looks like. For example, here we have the green and red points mean that Esca has been rated by an expert in the field. And then we can go here and look at the images immediately to see, okay, we have this yellow hotspot here, and then we can click on it and we can see, okay, how reasonable does this look like? And it's also a bit, it's made so that an expert that knows how Esca looks like can use this image and see, okay, is this actually, we can zoom in a bit, zoom around, look at also pictures of the pictures that are next to it that are supposed to have a little bit of overlap with that. So an expert that knows how Esca looks like can take a look and say, okay, you know what, this is actually just another disease, or it's just a dead dry plant or something like this, and get a lot of information immediately to judge how well the model performed and to throw out obvious false positives right away. Yes, so this is quite interactive, and you can see here, click around, look at the images, zoom in and out, and a result like this, based on a quick upload, could be computed within only like within a very short time frame of like 10 to 20 minutes. Yes, so this is the image detection part, and we can then go a step further and do the 3D reconstruction with photogrammetry. You can see a little example here. It looks a bit, the point cloud looks a bit rough, but basically each blue rectangle here is an image with the perspective in 3D space. So you can see here in black, the little black lines are the normals of the camera. And with this 3D reconstruction, we get a point cloud representation of our vineyard. So now we can classify this point cloud. So to go through the steps, we have very, very high, or like, can go very high with the resolution. Here it's obviously not that high, but we have a high resolution image, for example, of a plant with a stem. Then we do our AI-based image segmentation, which means for each pixel we get a class. In this case, it's red for stem, and whatever for no stem, so transparent for no stem. Then we do a 3D reconstruction, so we get a point cloud representing the plant with all their elements, which you can see here. Then we project the semantic content of these images onto the 3D point cloud. So each point gets a class. Here in this case, it's stem or no stem. So the stems are in red. Then we can do the same for many rows. We have just a smallish, medium-sized subset here. And then we have basically an accurate representation of the stem. We can then go ahead and do this not only for stems, but for arbitrary things, like, for example, we have the raw data on the left column. Then in the second column, we have the stems in red. Then we can detect also grapefruits, like in violet here. And then we can detect Esca disease, which we have in orange on the right side. For example, you can see here the raw point cloud. Then we have the grapes, and then we have the stems, and then we have the leaf disease. To show you a bit more interactively how this looks like, here's the visualization in Cloud Compare. So I can play around a little bit. I can remove all the detections and show you the raw point cloud. So it looks a little bit rough, but you can actually already visually see a lot of the diseases if you look a bit more closely, and you can see the stems and you can see the posts in between. And then I can turn on and off our segmented features. Like, for example, you can see the grapes here in purple. Can zoom in a little bit. Obviously, this is not work that a farmer would do, because this data is very rich and needs a lot of expert knowledge to then derive further higher level data from it. But you can take a close look and see it's very important to take a close look to see how well it works. And these are the grapes. Then we have the stems, and we can then go ahead and remove all other point clouds elements, and then can see the stems. And we can then do the same for our disease and can immediately see the hotspots. Okay, so this is then the point cloud with the semantic information. And based on this semantic information, we can then derive higher level products that can be very useful for the farmer, and which has, again, very can have lots of use cases. For example, here we have symptom maps, and then they can see accurately where there are symptom hotspots, and can go out in the field and check on whether it's just false positive, or if it's actually a true disease and they have to act on it, and then they can act right away. Yes, and now I give back to my colleague Miriam.
Yes, thank you. So what we then do is to bring these data partly to the next level, or do other analysis on the drone level. I will just give you very short information about this. So here you can see some of our drones in the field, which we use also for Esca mapping, or also creating other maps to extrapolate a bit what was shown by Mario. Can you go to the next slide, please? So here you can see, for example, this is the data Mario showed you, where you have the Esca disease severity, and if you compare it to field data, which is usually collected by our colleagues, collect reference data, then you can see the vine is growing in several directions, and it's really difficult to locate and combine field data with UAV data. But with this image acquisition in situ data collection, you have a better representation, and you can then train your data, your UAV data, and extrapolate it to unknown reference. You could continue. As here as an example where you have disease severity, and then you can combine it and classify it afterwards in contrast, which is working better. You can see it's growing mainly partly in gaps, and then maybe you have a misclassification. For the next slide, another use case is to detect, for example, management like pruning system or interspace growing, and to analyze this for the effect on drought stress or heating up of your field. For example, if you have less pruning, it might cool down your data or your field in drought stress periods. Here you can also see UAV data, which is used for analysis of heterogeneity. You can apply with this data, with changing the perspective to the bird eye perspective, you can apply different measures to reduce the heterogeneities in the field. So I will now come to the last slide and to the take-home message. So we have we use state-of-the-art sensors and image-based algorithm, and we can create an ever-increasing amount of data which can be used to monitor vegetation and to create digital vineyards. And this we can do on different scales, from the leaf to the plant to the field scale or even to the regional scale. And by using connectivity solutions and precise RTK systems, we can create very fast uploads and fast close to real-time data, which can be used either for research or for management by the farmer. And with this, we bring research and wine growers in a position to support their reaction and management to work on disease and disease management or planting or working against local heterogeneities and all other effects which appear by these extreme weather conditions introduced by climate change. And with this, I thank you very much for your attention. Please collect all your questions in the chat, and we can answer them in the Q&A session afterwards. Now I would like to hand over to my colleagues from Turkey. So, Mehmet, you can please share.
Sorry. Oh. I'm trying to. Sorry. Hello, everyone. I am Mehmet from Olive Research Institute. I am very pleased to have the opportunity to inform you with this presentation about work we are carrying out. I am here to talk to you about one of the major pests in olive production, the olive fly, and how the COMMECT project is offering a modern solution to manage this pest using digital technology. First of all, I would like to say a few words about COMMECT project. We are one of the partners in this project as the Olive Research Institute. The other partner from Turkey is Turkcell. They are responsible for telecommunication part. We are working mainly on an innovative approach to observe the olive fly using the digital traps and smart pest management technologies in this project. The project represents a significant step forward in pest control, as it combines sustainability with advanced technology to support our farmers and stakeholders to protect their products efficiently. Before talking about the specific of olive fly and our project, let me give you a bit information on the importance of olive production in Turkey. Olives are very important tree, mainly in Mediterranean countries, and Turkey is one of the world's top producers. Olive trees are grown across the country, from Aegean region to the Mediterranean region, with millions of tons harvested annually. Whether the producing high quality olive oil or table olive for direct consumption, the olive industry significantly contributes to both local economies and exports. However, like any other agricultural product, olive are at risk various pests, and the olive fly is one of the most challenging pests faced by olive growers. Now, I would like to give some information about olive fly. The olive fly is a small insect measuring about 4 to 6 millimeters length, with a shiny brown and yellowish appearance. It can be small, but its impact on olive crops is not minor. The olive fly lays its eggs on olive fruits, and then when the eggs hatch, the larvae begin feeding on the olive flesh. The feeding process damages the fruit, affects both quantity and quality of the harvest, but the damage doesn't stop there. If you look at it from the table olive perspective, which is harvest for direct consumption, the presence of olive fly leads significant issues. The most important damage is physical. The larvae feeding inside the olive fruit make some unpleasant spots on the fruit surface. The visible marks make the olive unacceptable for the table olive market, where appearance is very important. Other important damages is spoilage and decay. The damaged olives are more likely to be infected by microorganisms, accelerating the decay process. This leads to fruit falling off the tree before harvest, causing pre-harvest losses. The remaining fruit often has to be thrown away because it's too damaged to use. As a result of this damages, economic losses are very inevitable. Farmers are often find their crops harder to sell because the damage, meaning that they can't get the price what they expect. Even worse, some of olives are completely wasted. If you consider the issue from the olive oil production perspective, the olive fly poses a serious threat as well. The main problem is high acidity. As larvae feed on the olives, the oil that extracted tends to have a higher acidity. This downgrades the quality of the oil, potentially leading to a lower classification and negative influencing market price. It also causes lower oil yield. The fly also reduces the amount of oil that can be extracted from the olives. So not only does the oil quality suffer, but the overall oil yield decreases, reducing profitability for producer. What we are doing under this project, the project focuses on digital traps that are equipped with pheromones which attract the olive flies to the traps. Sticky yellow traps which capture flies. The high resolution cameras that take images from the trapped flies, solar panel and batteries, allowing the system to be energy efficient and independent of external power sources. As you see on the map, these digital traps are set up in olive orchards across key locations in Turkey, including Izmir, Antalya, and Mersin. The images of the captured flies are sent to a central system via SIM cards, enabling farmers to remotely monitoring the fly population in real time. Farmers can check the fly population without leaving their homes or farms. The system sends real-time images that are observed whether the olive fly population reach a certain threshold, and the time is determined for action. This approach minimizes unnecessary pesticide use, helps farmers monitoring pest activity, and allow them to take action on time. In essence, this system is a way to making pest control smarter and more sustainable. Farmers no longer have to guess when to spray their orchards or rely on outdated methods. Instead, they have access to real-time data-driven decisions that maximize crop protection and reduce their cost. One of the most important aspects of project is ability to detect olive fly population early. This allows for interventions to be made before flies have caused significant damage. Instead of applying pests based on a fixed schedule, farmer can now spray when the system alerts them to the population is high enough to cause harm. This system is designed to minimize pesticide use. By applying targeted treatment only when necessary, farmers reduce the environmental impact and also reduce the cost. This method leads to favor chemical in ecosystem, resulting in healthier soil, favor pesticide residues, and less harm to non-target organisms. By controlling the olive fly population effectively, the system helps maintain the quality and quantity of the olive harvest. This means a farmer can produce olives that are not only visually appealing but also the high quality, which means high market price for table olives and olive oil. The use of digital traps allows farmers to monitor pest population remotely, saving their time and effort. They no longer need to make frequent field trips to check traps or assess pest population manually. The project promotes eco-friendly farming by integrating modern pest management tools with sustainable practices. It empowers farmers to protect their crops while protecting the environment. Now, looking at the future of pest management is even more promising. After completion of this project, progressive steps will be added to these studies. The most important step will be AI integration. We will work to adapt artificial intelligence studies, which are being used in many areas today, to this project outputs. AI could automatically analyze images from traps, identifying olive flies without human intervention. This would significantly reduce the need for many manual checks, making the system even more efficient. Our project outputs can expand into other pests and crops. While the focusing has been on the olive fly, this system has the potential to be adapted to manage other pests in olive orchards or other crops. By extending the technology, we can increase its utility across various agricultural sectors. Predictive models are another topic. Using the data collected from digital traps, we can develop predictive models that forecast pest outbreaks based on environmental factors like weather, soil condition, and historical pest data. This would allow farmers to act proactively rather than reactively. Farmer education is necessary to make these new methods aware to ensure the full potential of the system is realized. We will continue to offer training and education programs for farmers. This will empower them to use this technology efficiently and integrate it into their daily farming practices. Last but not least, policy support and scaling. Collaboration with policymakers and agricultural organizations will be crucial. By advocating government support programs and financial aid, we can make this technology more accessible for farmers across Turkey and other Mediterranean countries. In conclusion, the COMMECT project represents an innovative development in the way we manage pests of olive orchards. By combining digital technology with sustainable pest management, it's possible to reduce chemical use, improve the quality and yield of olive trees, and protect the environment. This system is not just a tool for farmers. It's a step forward, more sustainable agricultural practices, and can be adapted to other crops. Can be adapted to other crops and regions. The future is bright for pest management in olive farming, and we are excited to continue innovative and expand this solution for more sustainable and successful agriculture. That's all I would like to give information about our project, and thank you very much for your time and attention.
So I would like to, first of all, thank a lot all the colleagues, Miriam, Mario, and Mehmet for their detailed presentation. And I'm glad to see there was interest from what I can see in the chat, in the Q&A. We collect already some questions, and we can start from this, but I invite everyone to not be shy and to raise more questions. So, Mario and Miriam, we received some question related to, let's say, the need of having a 3D representation to detect Esca symptom, and if it is really needed or it is enough to have a 2D scene. And this question was raised by Matthias Selsbo. I hope I pronounced well the surname. I apologize if it was not the case. And he was also wondering if we work closely with the farmer. This is the case indeed. And finally, he was wondering if, okay, based on the data that is available, we can help the wine grower giving like advice on decision to take or new practice to adopt. And we can start from this.
Yes, I think the first question Mario probably would like to answer with the 3D reconstruction. No.
I'm not sure if I see all the questions, but they seem to be more or less all about this. So yes, it is a very good question, and it also highlights a bit the flexibility of the approach. What does the 3D reconstruction add? It's not very, it really depends on the use case. If, like, let's say a farmer only cares about knowing roughly if there's a disease somewhere in the field. So if he only cares about which row it is in, or stuff like this. We don't really need the 3D reconstruction at all, because it's enough that we know, okay, there is a symptom detected over there in this row, roughly at this position. But if we have a use case where high precision is required, we don't want to know where the image that shows the symptom was taken from. We want to know where the symptom is and not where the image is. These are two different things, and there can be a difference of 1 meter, 2 meters, depending on the observer angle of the camera. If it's very oblique, it can be even more than 2 meters. So if we have a use case where we need high spatial precision, like for example, where you're trying to save costs on spraying pesticides or fungicides or something like this, so you don't want to spray plants or leaves even that are not infected, then you need to know exactly where the symptom is and not where the image was taken from. Or, and this is actually where I am coming from, you have a use case where you want to compare UAV data with data taken from the ground, and then it's not enough to know that a given plant in a given row is infected. You have to know where the symptom is in order to be able to detect it from the drone, or to test if your drone detection is correct. So in these use cases, we have to know exactly where the leaf is, down to, I want to say, an accuracy of very few centimeters. And then you need the 3D reconstruction. So we don't need it for the 3D aspect. We need it to have better localization in 2D. Yes, but it really depends on the use case, and the approach is flexible enough to say, okay, we don't actually need the 3D reconstruction, which saves a lot of time. The 3D reconstruction is actually more computationally intensive than the AI recognition of the features. So I hope that answered the question. I'll be happy to take follow-up questions.
I will invite Matthias to take the floor if he need to ask more, and if he's satisfied, we can continue with the next question.
Hi, I'm satisfied by the answer. Well, quite. I would love to dig more in there, but I don't think it's the time and moment, so we can do that later. Thanks.
Yes, let's follow up. Okay, then Miriam, did you want to complement the other question related to how we can help the wine grower and our collaboration?
Yes, I can answer this question. So in general, to have this applied by farmers, we have few farmers which we say pioneer spirit. They also come to us and ask questions, and then they are using it mainly also have a look at the data. So we really start with rather little details and more basic products, but there are some which are really interested also having such kind of data for monitoring over several years to see their effects in the fields. And what we also do to bring it more to practice is that we more work also with other companies which then offer already some digital tools for wine growers and integrate our data there and offer it via this way to the wine growers. And what are new practices or decisions? So example of trunk surgery is not applied in our region, for example. So but then we come from two sides. First, we also introduce these management practices, and at the same time we also show data, how the management can be applied in the field, how maps can be created or that maps can be used to apply this measure in the field. But here, yes, it's also, let's say, a journey. It's not that you offer a new practice or new tools and then it's immediately applied. But also like new decisions can be introduced, like for example, irrigation is not applied yet. And with such kind of data, you could also plan it on a regional scale. So this would be a new practice, which is not new at all, but new in our region. And then we can use such kind of data to have more a strategy behind, for example, yes, using the source water for irrigation.
Thanks, Miriam. Since time is running out, I would like to continue because Feras Youssef had some additional question. I think the first one is for Mario. He was wondering about the duration of the processing time and for building the map. And the second question, still from Feras, is more for Mehmet. He was wondering if the method that we are adopting can help as well in detecting another disease, the peacock eye spot, that is also spread in olive production. So I guess we can start with Mario.
Okay, yeah, processing time, of course, it's a very complex topic and it relates a bit to this, of course, to this aspect, do I need 3 data or not? Do I need the 3 reconstruction part or not? I already said that the AI feature detection, image segmentation part is much less computationally intensive than the 3D reconstruction. And it also scales differently. So if I just don't use the 3D reconstruction at all, I can go image by image, and it also scales super linearly. So if I have twice the amount of images, it will just take twice as long, which is not true at all for the 3D reconstruction because there's lots of other aspects to consider. How's the alignment, how's the overlap between the images, and it can grow quite fast, and I basically have to rely on making smaller subsets to do the 3D reconstruction. Just to give a rough idea of how long something like this would take, doing the Esca detection on the images for a single row is a matter of minutes. So it can be also, it can be single-digit minutes for a single row. But for the 3D reconstruction, it would be more like talking about hours. So there's a very big difference between the processing time of these two. But also lots of potential to go lower. For example, we could reduce the image resolution and could get, if time is a tough constraint and we need 3D reconstruction, we could try to find ways to improve the speed a bit, but that's roughly the difference of time we're talking about now.
Thanks, Mario. I will ask Feras if he's satisfied with the answer. Maybe, Mehmet, you can follow up on the question related to the disease, the peacock eye spot.
Thank you, Yusuf, for this question. It is a really good question. And as you know, Maria Rita, we don't work just olive fly, but also peacock eye spots under this project. But this webinars is about just only our projects, a part of projects, image monitoring, pest monitoring with image system, and we have also some task about this disease. And we have some information, but it is not possible to explain everything during this meeting. Maybe we can make another webinar about this topic and we can give information, but I can say just we are also working for this disease under this project. And we have some results, but it is not completely finished, and I cannot say anything now.
Okay.
Thank you.
So this is only like to give you a flavor of some of the work done, and the idea indeed is to continue the discussion after, and you can get in touch with us, and
Yes.
of course we are happy to share additional information. I don't see additional question in the Q&A chat, but of course, if someone want to add additional comment also related to similar activity you are doing in your project, we are glad to share. You can raise your hand and ask directly. Yes, Matthias, please.
Since we have 5 more minutes, about the quality of the images. I've seen that you're using phones to do this. Do you think we need a better quality of images than the one from a phone in terms of pixels, but also in terms of acquisition speed, like the frequency of the images? Do you think there is a particular need regarding to that? Thanks.
Yeah, I can try to answer this. I have not, I mean, obviously in the context of UAV image acquisition, I have experience with other sensors, but with terrestrial acquisition, I don't really. The rough idea is that I think for the feature, for the image segmentation part, I can't imagine that it matters a lot. We can go resolution-wise, we can always go higher. That's not a problem. I think photogrammetry-wise, I think it could be much improved with a better image sensor, because that would facilitate the photogrammetry and the feature detection and type point detection a lot if we could rule out image distortion effects and shutter effects and stuff like this. So the photogrammetry part, I imagine, could be improved greatly with a better image sensor. The image segmentation part and AI detection part, I have a hard time imagining that it would make a difference. Does that
makes sense? Yeah, that makes sense. Thanks.
And I guess in general we can a bit play with the resolution and the need of the application. And then I would like also to mention that we did some tests changing the resolution to test to demonstrate that okay, up to which extent we could acquire the video in real time. And we played a bit as well with the duration of the video, considering single row, multi-row. So I guess the product is there and can be customized based on the need of the application.
Yeah, and just maybe to add one sentence to this, why a smartphone? And if we design a system, we could take any sensor really. We come from a different monitoring context where it's kind of important to have a very simple, also not super expensive handheld device. So that's where we're coming from and why we're using a smartphone.
Yeah. But indeed, it is not limited. We could use another type of camera. Okay, so I want still to take the last few questions. It was Feras asking Miriam about the, let's say, different scale drone for regional scale, and then he was asking about the kilometer and size. Maybe you can take this last question.
Yes, like always, the answer is it depends. So for regional scale, we do not use drone images. We call regional scale rather like really in our case, it's the entire wine region of Luxembourg, which is not huge. Luxembourg is small, but here we are using satellite data. For the field scale, we are using drones. Here we also have rather small fields of few hectares, and there it takes, let's say, also few minutes to acquire the images of one small field. But of course, you also need to go there. You need, best case, good weather condition. You unpack your stuff, and also the processing of these normal cameras is rather short. So you can have in few hours, minutes. So in the same day, usually you can have a first analysis. But if you go deeper, and also we also do chlorophyll estimation, we also have hyperspectral camera, then it takes again more time. And for regional scale, as said, we are more using satellite data. They are partly free of charge, or Planet Scope with a bit higher resolution costs a certain amount of money. And then, yes, you can analyze several square kilometers. Again, depends if you just want to have a rough analysis of vitality of your fields, what we, for example, do to analyze first, compare drought stress on a rather coarse scale. Then it also does not take much time. You can produce for our entire region within half a day or less, 1 to 2 hours. You can easily download Sentinel-2 data and compute some vegetation indices, which gives you already for the entire region an idea of the patterns where you have more severe drought stress and where you have less severe drought stress. I hope this answers the question.
So thanks again to Miriam, Mario, and Mehmet for their presentation and all the information provided. And I want to thank all the attendees for the interest that they showed and for joining this webinar. Finally, I would like to thank all the members of the COMMECT Consortium, and please don't hesitate to follow us on our website, social channel, and as well to get in touch if you would like to discuss some specific topic or you have additional question. Thank you very much, and I wish you a nice rest of the day. Thank you. Bye-bye.
Thank you.
Thank you. Bye-bye.